We just completed a set of notes where we looked at the notational setup for a 2 by 2 contingency table, where for the columns we have some kind of response variable, which could be where we have two categories for that response variable. One category could be a success, a second category could be a failure. And we observe this response then corresponding to items that are within two different groups. Simply, let's call group 1 and group 2. Now, what we're very interested in this particular scenario is taking a look at the probability of success for group 1, the probability of success for group 2. And we like to be able to compare them in some way. There's a few different ways that one could do it. What we're going to focus on right here is to make the comparison through their difference, pi1 minus pi2. Now notice if pi1 minus pi2 is equal to 0, that says these probabilities of success are exactly the same. So it doesn't matter if an item comes from group 1 or group 2, the probability of success is the same. And so that's going to be one of the things that we're going to be interested in examining further here. Now, to look at this difference, pi1 minus pi2, we're going to form confidence intervals. Now, to form this confidence interval, let's go back to what we basically started off this chapter 1 notes with, and that is looking at one binary response, essentially in a homogeneous population situation. So our interest would be looking at pi, the probability of success parameter. It's estimated by its MLE, maximum likelihood estimator, pi hat. This maximum likelihood estimator, when we think of it as a random variable, has some nice properties to it. In particular, for a large sample, it has a normal distribution with a mean of pi, what we're trying to estimate, and a variance of pi times 1 minus pi over n, your sample size or the number of trials. So using this same notational setup then, we can write this then in our new notational setup, where all I'm going to do is add a subscript to my pi's. So pi hat 1 is going to be the MLE, corresponding to the estimated probability of success for group 1. It has an approximate normal distribution as well, with a mean of pi 1, variance of pi 1 times 1 minus pi 1, all divided by n1, where n1 is the number of trials for that group 1, or that sample size for group 1. And this all works out well if you have a large sample size. Pi2, pi hat 2 are defined in a similar manner. Now, we could rewrite this setup here in a little bit more of a compact form, and you will often see this done in statistics. We could say, let's say, pi hat, and that should be pi hat sub j. We could say that pi hat sub j, where j is equal to 1 or 2, has an approximate distribution that is normal. That's what the capital N represents, with a mean of pi sub j and a variance of pi sub j times 1 minus pi sub j, all that divided by n sub j. And this works out for a large n sub j. So now that we have the distribution for pi hat sub j, let's see if we can get the distribution for what we're really interested in doing, and that is, again, trying to estimate pi1 minus pi2. So what we could do then is look at the corresponding estimator, pi hat sub 1 minus pi hat 2. Think of this as a random variable, and what one could do is show that this statistic also has an approximate normal distribution to it, where the mean of that normal distribution is what we're trying to estimate, pi1 minus pi2, and the variance is simply the sum of the two variances that we had previously for pi hat 1 and pi hat 2. Again, this all works if you have let's say, a large number of trials for group 1 and for group 2. Well, where does this variance come from? Well, this variance can be shown through using some results from a mathematical statistics course. Again, I know a number of students have not seen that before, and that's fine. And so I wouldn't expect you to be able to do this derivation here. But really briefly, so what we're saying is that the variance of pi hat 1 minus pi hat 2, which is what we see here, is equal to the variance of pi hat 1 plus the variance of pi hat 2. Why? Well, it goes back to what is done in a mathematical statistics course, where if you had a random variable x, a random variable y, and some constants, let's say a and b, so these are numerical values, maybe like the number 3 or number 4. Then the variance of a times x plus b times y is a squared times the variance of x plus b squared times the variance of y. If you've had a mathematical statistics course before, you might be wondering, well, where is this covariance term that you would normally see also out here? Well, that's not there because remember what we have here is independent binomial sampling. So x, well, at least in our case for pi hat 1 and pi hat 2, x and y, when they're independent, we don't have to worry about the covariance. It ends up being 0. Okay, so now let me do a little bit of erasing here. So how do I estimate then this variance that we see here? Because again, relies on population parameters. Well, when I estimate it, then of course now my notation becomes a var hat for an estimate. Var hat of pi hat 1 minus pi hat 2 is exactly what we see for the actual variance, except for now we put hats on top of the unknown parameters. So now that we have this, we can then form a Wald confidence interval similar to how we did for a Wald confidence interval for just pi alone. We take the estimate plus or minus a quantile from the standard normal distribution times the square root of that estimated variance. And that's our Wald interval. Now, hopefully you remember from when we were doing a Wald confidence interval only for pi itself, we showed that there were some problems with it. The stated confidence level, like 95%, was rarely achieved with that Wald confidence interval. In fact, the true confidence level was often much less than what the stated confidence level was, and that's why we wouldn't want to use that interval. And as you might expect from this name for Wald confidence interval, now for pi1 minus pi2, the same thing occurs here, unfortunately. So despite this interval often being taught in introductory statistics courses, I mean, I would expect that a lot of you have already seen this interval before, maybe not talked about how it came about though before. Despite it often being talked about in these introductory statistics courses, this interval should not be used in practice. Instead, my recommendation is to use what's called the Agresti-Caffo interval. So this is Alan Agresti and Brian Caffo. They came up with their own idea for a confidence interval similar to the Agresti and Kuhl interval that we saw before. And what they say is basically form a regular old Wald interval, but use adjusted estimates for pi1 and pi2. Let's call these adjusted estimates pi tilde 1 and pi tilde 2. And look how we're making the adjustment. So W1 is the number of successes, you could say, for group 1. I'm going to add a constant, just 1. So notice what we had before with the Agresti-Kuhl interval. We didn't have a 1 here, but rather we had some quantile based upon the standard normal distribution. Now what Agresti and Caffo say, just put a 1 there instead. Then the denominator, we have n1 plus 2. So essentially what we're doing is we're adding 1 success and 1 failure, so a sample size of 2, to group 1. And we do exactly the same thing for group 2. Now you might be wondering, why did they decide on always adding overall 2 successes and 2 failures to the data? Well, they actually looked at some other adjustments and they found that this one worked the best. So with these adjusted estimators then, we can form what's like a Wald interval. Pi tilde 1 minus pi tilde 2 plus or minus the quantile from a standard normal distribution times the square root of an adjusted estimate of that variance. So again, this will be the interval that we will be using. Okay, so let's look at how we can compute this interval. So we're going to go back to the Larry Bird data again. And remember what we're interested in this particular situation. Pi1 minus pi2 would be essentially the probability of success on that second free throw attempt. Given that the first one was made, let me restate that. We're interested in the probability of success on that second attempt, where we have two groupings. We have one for the first free throw was made, and we have one for the first free throw was missed. We want to know, in the end, doesn't matter what happens on that first attempt relative to what happens on the second attempt. So we are going to be interested in doing a confidence interval for pi1 minus pi2 in this particular situation. Okay, so a little bit of review from our last set or some previous notes. We're going to form an object called C.table. This stands for contingency table. This is where we're going to put our data. We can use the array function to form this contingency table, where the data argument corresponds to our data, the 2 by 2 part of my table, where I enter in the data by column. Again, it's a 2 by 2 contingency table, and I use dim names to put some nice labels associated with the dimensions, the rows and the columns. So here's my actual contingency table right here. And from that, we've also saw how we can form a table, an object that we call pi.hat.table, where basically what we have here is pi hat 1. We have pi hat 2 right there. What I can do is I can pull the pi hat 1 and pi hat 2 out and form pi.hat 1 and pi.hat 2. Okay. Now, to do our calculation for our interval, we need to basically, again, put this the equation that we saw for the Wald interval, put it into the correct form in terms of our syntax. This is very similar to what we saw for confidence interval for pi. First, I create an object called alpha that contains my alpha level, 0.05. Then, again, similar to what we've done before, we form an object called var.wald, which contains my pi hat 1 times 1 minus pi hat 1 divided by n1 plus, and I do the same thing for pi hat 2 times 1 minus pi hat 2 divided by n sub 2. Then I form my interval, pi.hat 1 minus pi hat 2 plus the quantile from the standard normal distribution. Remember, I'm going to have two quantiles here, a negative version and a positive version. For alpha 0.05, this is going to be negative 1.96, positive 1.96. Take it times in the square root of the var.wald. And just as a little bit of a reminder, let me come back over here to 10 now. You know, again, you can execute segments of this code to help you understand what's going on. So if I look at that pi.hat 1 times 1 minus pi hat dot 1 slash the sum of C.table, the first row, oops, let me actually redo some stuff up here first, excuse me. I was running some code before actually doing this video here, and so some things had changed. Okay, there we go. Okay, so let's look at this variance equation once again. So the sum of C.table left bracket 1 comma, what that's going to give me is my n sub 1. So just to see that, how about we take a look at C.table. So there's my contingency table. And what we've seen before, if I just use 1 comma within brackets there, that's going to give me my first row. And so if I say sum of everything that first row, I get my n sub 1. I combine this with pi.hat 1 times 1 minus pi hat dot 1, divide by n1. And there's a portion of my corresponding variance. If I run the whole thing here, we can see my var.wald is this. And if one wanted to, since this is a fairly simple example, one could actually, you could say, do by hand calculations that to verify indeed that R is doing what you would expect. Okay, so let's talk about the Agresti-Caffo interval now. I need to form my pi tilde. So pi dot tilde 1 is going to be W1, 251, plus 1, that quantity, then divided by n sub 1 plus 2. So let's go ahead and do that. And I could do a very similar thing for pi dot tilde 2 as well. Okay. Now to form that variance, called var.ac for the lack of a better name, and basically have exactly the same expression here, except for now I have pi tildes, and I make that small adjustment to the number of trials, the sample size for each row. Then I can form my interval as well, and here's my corresponding interval. Okay, so let's go back to my notes. Hold on a second here. Okay. So my 95% Wald interval is negative 0.1122 all the way up to 0.0623. My Agresti-Caffo interval has a little bit of a different lower bound and also a little bit of a different upper bound as well. So if I wanted to have a standard interpretation here of, let's say, the Agresti-Caffo interval, I could say something like, with 95% confidence, I would expect the difference in the probability of success for the second attempt to be between negative 0.1035 to 0.0778. For, let's say, group 1 is my first free throw made, group 2 is my first free throw missed. Okay. Now, if we also take a look at the interval, notice that 0 is actually within the lower limit and the upper limit. So what this is saying is that pi1 minus pi2 could be 0. Putting this into the context of our original interest with this data, what this says is that pi1 could be equal to pi2. Thus, in terms of the population itself, what happens on Larry Bird's first attempt might not have an effect on what happens on his second attempt. Therefore, we do not have sufficient evidence to indicate that the outcome of Larry Bird's second attempt is dependent upon what happens on the first attempt. So that's kind of an interesting thing that occurs here. Notice it does not mean that indeed pi1 minus pi2 is equal to 0, because we can see that there are other non-zero values that are inside that interval. So what are some other ways that one can actually perform these calculations? Well, there is a package in R called prop.cis. Let me actually get to that portion of the program. There's a package called prop.cis that does these calculations somewhat automatically. Now you might be wondering, well, why didn't we just start off with that to begin with? Well, there's two reasons. First, it's good to understand what the corresponding equations for the confidence intervals, what they actually mean and how to work with them. And second, this prop.cis is a user-contributed package. And with any user-contributed package, just because it's available on the R website or the comprehensive R archive network, does not necessarily always mean that everything is, let's say, okay inside that package, meaning that the calculations are done correctly. So for example, when I was putting together my first edition of my book, there were a number of packages that I encountered that did not produce the correct answers. How did I know that? Well, I did these calculations the long way first to make that verification. And so that's why, especially in situations where the calculations are not too difficult, it's good to know how to do, let's say, the long way. And once you're comfortable with then some of these other packages that will do it a little bit easier, then you can go ahead and use them. Okay, so in this particular package, there's a function called Wald2ci, where the x1 argument for this function allows you to enter in w1. The n1 argument allows you to enter in our n sub 1. And then you have an x2 argument and an n2 argument that are similarly defined for the w2 and n2. I specify my conf.level, and then adjust corresponds to the confidence interval type. In this particular case, I'm going to use the Wald interval. The reason why it's called adjust is because when we do the Agresti-Caffo interval, we can use adjust equal AC for that, which is like an adjusted interval. So let me go ahead and run these two segments of code. Let me just also mention before I forget. Notice when you do use the adjust equal AC, you still use your regular old N1, your regular old N2 in here. You do not make the adjustment yourself. The function does it for you. And so if I run that code, we get exactly the same intervals as what we saw previously. Okay. There are many different ways in R where these intervals can be calculated. On your own, you can take a look at this additional function called prop.test. This actually exists in the stats package, which is automatically installed in R itself. Prop.test can do the Wald interval automatically for you, and through a simple adjustment, you can do the Agresti-Caffo interval as well, as shown in my program. Okay, so let's move on here to a new example. So earlier in this set of notes, in this video, I mentioned that the Wald confidence interval has problems achieving the correct confidence level, just like what we saw for a Wald confidence interval for pi itself. Let's look at that more closely now. So let's consider a situation where N1 and N2 are 10, so just 10 trials. Pi2, meaning the probability of success for group 2 is 0.4, and I'm going to form 95% intervals. On the y-axis of this plot, I'm going to have the true confidence level, and on the x-axis, I'm going to put various values of pi1. And so what this plot represents is very similar to what we saw before when we were just doing a confidence interval for pi. This gives me my true confidence levels as a function of, in this particular case, pi sub 1. So if we take a look at one particular example here, let's take a look at, let's say, pi1 is equal to 0.4. So notice pi1 minus pi2 in this particular case, since pi2 is equal to 0.4 as well, pi1 minus pi2 would be 0. So the confidence interval can be thought of as as working, let's say, if 0 is inside the interval. And if I project up at pi1 equal 0.4 and then come over, what we can see is the true confidence level for the Wald interval here is only about 90%, even though the stated level is 95%. And if I keep on projecting up until I hit this line that represents the true confidence level for Agresti-Caffo, we can see the true confidence level there is about 0.955 or 0.96, right around there. And so we can see that in this particular case, when for pi1 equal 0.4, the Wald interval is liberal, the Agresti-Caffo interval is a little bit conservative. I would use that Agresti-Caffo interval every single time based upon what I see here. Now if we look at other values of pi1, we see a similar trend that occurs. In fact, the Wald interval never, ever gets up to the stated confidence level of 0.95. That's not good at all. So again, that's why the Wald interval is a liberal interval here. The Agresti-Caffo interval, though, its true confidence level tends to bounce around 0.95. It's probably between at lowest 0.94, highest maybe 0.96, 0.965 or so. And so therefore, this interval, it would be tough for me to say across all values of pi1 if its conservative or liberal, but definitely I would prefer this interval over the Wald because I know my true confidence level is much closer to the stated level. Okay, so how is this plot done? Well, it's done in a very similar manner to what we saw earlier for a confidence interval for just pi itself. And so to help you understand this, let's consider the situation where pi2 is 0.4 again. pi2 is 0.4, pi1 is 0.4 as well. So this particular situation I was referring to earlier. And let's now relate what we saw before for a Wald confidence interval for pi alone, how we found the true confidence level. Let's relate that now to now for the Wald interval for pi1 minus pi2. And so what I did here was basically I kind of copy and pasted some descriptions from earlier in my set of notes. And I left some blanks here so that we can basically see how what we've done before can now be modified for what we want to do now here. So step 1, define the true confidence level in this particular situation. Step 1 says find all possible intervals that one could have with W1 and W2. And so in other words, what you could think of this as, suppose we form a table. I have W1 here, I have W2 here, and let's say W1 is 0, W2 is 0, and let's say I want to find the confidence interval for that particular case, so whatever it might be. Then W1 is 0, W2 is 1, I find that corresponding confidence interval, and I keep on doing this until I reach N1 and N2, meaning I have all successes for group 1 and all successes for group 2, and I go ahead and find that confidence interval. That's all I would need to do. So in this particular case then there would be, since there's 11 different possible values, unique values for W2 and also for W1, 11 times 11 or 121 different possible combinations of these W's. Then step 2 here, what I need to do is find my my indicator function like what we saw before. This is going to be a function of W1 and W2. This indicator function tells me, does pi1 minus pi2, is it in the corresponding interval or not? So what I can do is form another column here referring to this indicator function. And if the interval contains pi1 minus pi2, in this case would be 0, if that interval does contain that, then I have a 1. Otherwise I have a 0. And so I look at all these intervals here to make that determination. Lastly here, calculate the true confidence level. Now to do this, what I need is the probability of W1 is equal to a particular value of W1 and W2 is equal to a particular value of W2. I need to find that probability. Well, what is that probability? At first you might be thinking, you don't know, but actually it's very related to something that we already do know. Because we have independent binomial sampling, we can break this joint probability up into these smaller probabilities that we do know how to find. This probability here is just a probability from a binomial distribution where we observe a particular number of successes, 0, 1, 2, or whatever, and a probability of success of pi1 with trials of n1. This probability here is exactly the same, but now for group 2. So all I need to do to find this particular probability here is multiply them together. So now to find this true confidence level, all I need to do is take what's in my indicator column, it's going to be a 0 or 1, multiply it by the corresponding probability. Do the same thing here, take what's in the indicator function column, multiply it by the corresponding probability. I do that throughout, and then I add up then all of those probabilities that are essentially all the results that are non-zero in the end. That's how I find my corresponding true confidence level. So on your own, what I want you to be able to do is actually write out a mathematical expression here that's a function of the indicator function and the corresponding probability, similar to what you saw for a true confidence level for just pi itself. Okay, now one thing that I want to come back and mention here. How I actually did this plot in R is in my program conf level 2prob.r. I want you on your own to run through that set of code. The reason why I'm not going to go through it directly here in this video is because it's very similar to what we saw previously for confidence interval for pi, and I went through the actual steps that are essentially programmed into R for it. Now, for those of you who are taking my course then, if during one of our in-person classes, if you would like me to go through that program, just let me know and ask, and I'll go through it in class. Now, you might be also wondering here, well, hold on a second here. What about other values of n1 or n2 or pi2? Do we get the same kind of plot? Well, no, we don't, but we basically reach the same conclusion. So consider a situation where now we change n1 to be 40, we change pi2 to be 0.3, we keep n2 at 10. This is what we get. Notice how the Wald interval doesn't even come close to that 0.95 stated confidence level. Notice also how well the Agresti-Caffo interval performs. It's really hugging that 0.95 line. Pretty good for most values of pi1. Now you might be wondering, well, okay, here this is conditioned on pi2 being 0.3. What if you allow pi1 to be anywhere between 0 and 1 and pi2 to be anywhere between 0 and 1? Well, in order to do a plot like that, now we need to go to 3 dimensions, because now we're going to have a pi1 that varies, a pi2 that varies, and then also the true confidence level. So in my program, I show how to do this kind of a plot for n1 and n2 equal to 10 and alpha 0.05. Because this plot's a little bit more complicated, I usually don't require students to be able to reproduce this plot, but if you just run the code, you should be able to do it just fine. But I typically do not ask graded items on a test. Sometimes not on a project. I might ask a question on a quiz, though, regarding this set of code. So if that isn't clear, please let me know. Okay, so I've actually ran through the code here, and let me actually bring up one of the plots. So what we have here, if you see where my mouse is, we have possible values of pi2, ranging from 0 to 1. And then also, on the other axis here, we have possible values of pi1. It just so happens that R is labeling it up there instead. Here on what would normally be thought of as a z-axis when we plot in 3D is my true confidence level. And I draw a plane at 0.95 because that's what our goal is. We want a true confidence level of 0.95. And what I've done is actually plotted then the corresponding Wald interval true confidence level. And as you can see here, the true confidence level never, well, at least it doesn't appear so, ever actually reach 0.95 ever as I spin through this plot here. So the way that I'm spinning through this plot, this is in Windows, I'm clicking left on my mouse, and I'm simply dragging the mouse arrow there. And so we can see here that this interval is really, really poor. Now I did exactly the same plot for an Agresti-Caffo interval, and what we can see here, notice how the red there, which, sorry I didn't mention this before, is the true confidence level. The red is actually intersecting with the green plane there, drawn at 0.95. And so what we can see here is that, yeah, and this interval is working much better than the Wald. Is it perfect? No, but is doing a much better job. It doesn't get too far below 0.95, and when it does, it's rare. There are times where you can see up here it becomes quite a conservative interval, but otherwise it seems like it's doing a pretty good job here relative to the true confidence level. So it's kind of an interesting plot to see. So in conclusion, Agresti-Caffo, use that interval, do not use the Wald interval. Now, similar again to what we saw for confidence intervals for pi, there have actually been many different confidence intervals proposed for pi1 minus pi2. The main other confidence interval that's worth noting, and unless you hear from me otherwise, you're not responsible for this, is a score interval. We've actually already talked about score intervals before. Remember, the Wilson interval also has the name of a score interval. It's based upon the score statistic and inverting that particular statistic itself. Really briefly, how that would work in this particular situation. To do a hypothesis test of pi1 minus pi2 is equal to some quantity. Most of you have seen this kind of a test written before where d was actually equal to 0, but it could be something else other than 0. So pi1 minus pi2 is equal to d versus an alternative hypothesis. The difference does not equal d. One can form what's called a score statistic that looks like this. And again, at least in an introductory stat course, you would typically have seen this kind of a statistic before. The main difference is that d would be 0, and you didn't have this superscript there corresponding to the pi hats. So this statistic, let's call it z sub s, has an approximate standard normal distribution to it for a large sample. And up here in the numerator, we take pi hat 1 minus pi hat 2, and we subtract off then the actual hypothesized value of d itself. Actually, let me remove, you don't need the way that I've written this up, you don't actually need the absolute value there, excuse me. Now, in the denominator here, we have basically what's an estimated variance for pi hat 1 minus pi hat 2. You can kind of think of it that way. The main difference here is that rather than using the regular old MLEs, we're going to find MLEs under the null hypothesis restriction that pi1 minus pi2 is equal to 0, is equal to d. This is a much more complicated issue or problem to find this corresponding MLE. We do the same thing for pi hat 2 as well. Then what we do is we find the set of d values such that my test statistic is within inside what you would normally think of as the critical values for this particular hypothesis test. So we check, for example, if d is equal to 0, is z sub s between these two quantiles for my standard normal? If so, that value of d equals 0, is going to be within my confidence interval. Then go to, let's say, d equal 0.01. I do this calculation here. I check, is z sub s between my two, what we again thought of as critical values? If it is, then 0.01 would be inside my interval. And so that's how this process essentially works. Because of the more complicated nature with it, there is not a closed form expression that I can give you for what the actual confidence interval is. Meaning I can't write out like pi hat 1 minus pi hat 2 plus or minus something and find the interval that way. Rather, instead, iterative numerical procedures need to be used for any data that you're working with to actually find this interval. The PropCI package, if you're interested, does have a function that does this automatically. It's called the diff score CI function. Okay, so that concludes then this discussion of confidence intervals for pi1 minus pi2.